So now let's take a look at the acid-catalyzed hydration reaction. This reaction is one of three basic methods that we're going to learn that will allow us to add water to an alkene and convert that alkene into an alcohol. Now, the acid-catalyzed hydration is the simplest of those three and involves the addition of water in the presence of generally a strong acid catalyst and usually involves heat as well. But the result of the reaction is an addition of water where the OH group, assuming that the alkene is not symmetric, the OH group ends up on the more substituted carbon and the hydrogen on the less substituted carbon. So just like the HBr addition or the hydrohalogenation, the addition of water under acidic conditions is a Markovnikov addition. Now, acid-catalyzed hydrations do have somewhat limited use, and the main reason for that are the reaction conditions. The acid in this case is generally a strong acid, something like sulfuric acid or hydrochloric acid or phosphoric acid, all of which are strong acids. And so these strong acids, especially once you add in high temperature, not only can react with alkenes, but can react with alkynes as well as most carbonyls, including ketones, aldehydes, esters, amides, as well as possibly being able to react with a few other functional groups as well. So under the right conditions, acid-catalyzed hydration can be very useful. But usually that's only if there aren't any other functional groups present. So how does the reaction work mechanistically? Well, in many ways, it's very, very similar to the HX addition. If you recall, in the HX addition, the first step was the alkene attacking the HBr or HCl. Well, if you think about HBr, not only were they electrophiles in that reaction, but they're really just strong acids. And so, same start here. The alkene attacks the H+, the strong acid. That gives us two possible carbocations. We know we've learned previously with the HX addition that the more substituted carbocation is going to be favored. In this case, tertiary versus secondary. Once we form the carbocation, water attacks. To form this cation, which loses a proton to give us our product. And we can look at examples using other alkenes. In a case like cyclohexene, it doesn't matter which carbon of the alkene we add to. But again, if our alkene is not symmetric, then we know that the addition should take place at the more substituted carbon. So where might we see a hydration reaction get used? Well, probably the simplest and most important example of this acid-catalyzed hydration is the reaction of ethylene. If you take ethylene and you add sulfuric acid along with phosphoric acid, and you've also got to heat it up pretty high, you make ethanol. And ethanol, I'm sure we all know, is the kind of alcohol that you find in drinks. But ethanol also is very important as a solvent in chemistry labs. And so this reaction here is used in industry to make hundreds of thousands, if not millions of gallons of ethanol every year. Another example where we see a sort of very basic hydration reaction is this. So this is the conversion of fumarate to fumarase. And you can see that what we've done is on one carbon we've added an OH, one carbon we've added a hydrogen. Didn't matter which side because this starting alkene is symmetric. But again, the net result is the addition of water, and this is one of the steps we find in the citric acid cycle. So again, sort of to summarize, acid-catalyzed hydration, very useful in some regards, but you're limited to fairly simple molecules. And by simple, we mean molecules that don't have a lot of other functional groups. Because again, this combination of high temperature and strong acid means that there are a lot of other functional groups that can react as well.